Okay, I think we're ready to get going. Good afternoon, everyone. My name's Gavin Mudd. I'm the director of the Critical Minerals Intelligence Centre, which is a project delivered by the British Geological Survey for the Department of Business and Trade. Today, we thought we'd go through some of our key projects that we've been working on this year and really showcase some of the important research and sort of the various outcomes. So let's get started. First of all, just to explain a bit more about, I suppose, our background, why we exist and so on. But we are here to really help the UK government across the spectrum when it comes to critical minerals. A lot of that is finding data, synthesizing that data, analyzing it. And that starts with both primary mining through different supply chains, looking at the opportunity for secondary mineral resources, looking at different markets, some of the issues with those. And whether it's a focus on the UK, but also understanding that global context. And so a lot of that global context is geopolitics, which can lead to supply disruptions, but also the various environmental, social, and governance factors as well. So, as I noted, we're funded by the Department of Business and Trade to basically provide that broad support for the UK government around critical minerals. And one of the things that we always like to sort of highlight is that really critical minerals, applying criticality, it's really risk management. It's understanding the supply demand going on in different commodities and how different disruptions and the impacts on the economy may affect the achievement of different objectives we have as the UK or even as the globe as well. So that's the sort of the broad background. For us to be able to help with that, we do, obviously, a couple of years ago now, we released the 2024 Criticality Assessment of the UK, and that was an updated assessment across about 80 commodities, looking at not only the supply risk, but then also how vulnerable is the UK to particular minerals and so on. And so, and we've been extending our work this year, and you'll hear from that later on. Another big area is an important area is really saying, well, if we've got particular goals, whether that be net zero, the energy transition or the digital transition and others, what are the critical minerals that we're going to need to achieve those goals? And so that's looking at for much of 2023 and 24, we did a range of studies around decarbonisation and the future technologies required to achieve that. What are the critical minerals? So it's really forecasting the next 25 years worth of demand to basically quantify exactly what the UK needs, and therefore really, I suppose, help set the agenda for that. We look at a lot of the global landscape around primary supply, so that's mining, smelting, refining. We look at key trends. BGS, of course, has been publishing in World Mineral Statistics for well over a century now. So we've got, I guess, a wealth of experience. And it's not just a matter of pulling the data together, it's also analysing that and understanding what that means and trying to really provide some, I suppose, some knowledge and so on. Another major area for us is, of course, looking at the circular economy. And so one of the projects which we have been doing this year, but we are not presenting today, is taking the various foresight studies which are looking at demand and then quantifying end-of-life products in, say, 10, 15, 20 years, what that means for future secondary supply. So in other words, how can we start to model and quantify that future secondary supply? And so again, so that's a large area of work for us. And then we also do a range of different commodity deep dives. We might do some assessments of different countries or regions, perhaps. Again, all within the framework of thinking about critical minerals. So that's CMIC. Of course, the way we do that is just a conceptualization of the types of data and how it fits into various value chains or supply chains. And so can we see the primary side, you've got mining, refining, different stages of manufacturing to product use, and then eventually end of life. And there's various types of data out there. They're not always perfect, they're not always abundant, not always public either. Certainly at the start of the chain, we've generally got excellent data, thanks to our BGS efforts. But as you go further down the supply chain, the amount of public data generally decreases. So again, it's understanding all of the different issues at the different stages. So for today, we've got three major projects we're presenting on. So there'll be two presentations on the copper waste and scrap, and that's both the actual results side, which I'll be presenting, and then the policy implications and opportunities. Now, given we are in a pre-election period at the moment, we'll have to be careful in that. But I think we can present the work we've done and what that means with respect to policy. The next presentation will be, on the policy side, will be led by Jo Wragg from BGS. For the future of digital, this is where we investigated the materials required for quantum computing, artificial intelligence, and data centers. So that real nexus, and that work's been led by Holly Elliott. The next project is what we call the future of the criticality assessment. So basically, what are the new ideas? What are the issues that we can keep adding into the criticality assessment to make sure that it really helps us understand the supply risk and what that means for the UK economy and the goals that we have. And so that work has been led by both Pierre Josso and Richard Shaw, and Pierre will be presenting that today. We are planning on doing a recording. Recording is in process, so hopefully everyone is okay with that. That will be uploaded in the near future to our CMIC website. And after that, we'll have a quick Q&A session where we can answer questions about some of the science that we've done, noting, of course, that we are in a pre-election period, so we do need to be careful. And some questions we may take on notice, and then we can come back later on. So without further ado, one of the issues that we found during the criticality assessment was some of the data and I suppose some of the interesting little things that sort of get shown by that data. One of them, in looking at waste and scrap flows, you could see some interesting issues, I guess. One is that there seems to be a very strong export of waste and scrap containing copper leaving the UK. And so we wanted to dig into that. And we also found some other issues with some tungsten data, which we're not presenting today. But again, just trying to understand the data, understand how we can and can't use that data, and what that means for things like a circular economy, or maybe copper supply, and so on in the UK. So we set out basically to dig deep into the data around sort of copper and tungsten, but only showing the copper results today. But the basic problem at heart for copper in particular was something of the order of about 250,000 tonnes a year was going out in exports, and only about 25,000 tonnes per year in imports, and also a very small amount of actual refined copper. So it suggested that maybe the UK is actually a net exporter of copper. And if we think about the way that we go about criticality assessment, one of the key factors that we use in quantifying UK economic vulnerability is net import reliance. Now, if we're exporting a lot of waste and scrap, or an excess of waste and scrap, for example, does that mean we're really 100% net import reliant for that copper? So we wanted to delve into that to really understand what that data was showing, what it means, and so on. Now, for tungsten, the issue was a bit different, where the economic data suggests the UK is producing around about 20,000 tonnes a year, which is a fifth of the equivalent of global tungsten mining. All right, and so that's something that I think with the report we've been able to show that data is probably not realistic, and it means tungsten containing products, but certainly not high content tungsten products. So let's look at the results for copper. We start here. We can look at the last sort of decade of data, looking at what we call HS code. So if we're looking at international trade data, it's the harmonized system, and this is the code for waste and scrap, which mostly contains copper. And so we can see in the sort of the red here, we've got the exports. So, starting a bit higher, just above 250,000 tonnes, and gradually declining to just over 200. And our imports there fairly constant at around about 25,000 tonnes or so. Now, if you go back and the data, and again, because BGS has been compiling our world mineral statistics and looking at things like imports and exports for a long time, we can actually take this data back 100 years. Now, if we just look at what's called copper waste and scrap, we don't know exactly what the forms of that waste and scrap are. We don't necessarily know the exact copper content. But what is reported as copper waste and scrap goes back 100 years. And so we can certainly see that since the 1970s, we've had this big increase in waste and scrap copper exports, and really only a small amount of imports. So to delve into that and understand it is, I suppose, where we delve into a lot more. Let's look at the main copper codes. So if we look at the primary forms, we can see on the positive side, on the top half, they're green. So the darker green is refined copper, so wrought refined copper. The light green is unwrought, unrefined copper. So that needs further processing to make it usable for different products or components. And we can see on the bottom, that's the negative side, that's exports. So that's stuff that's leaving the UK. Now, this is just the primary form. So we've got alloys, refined, unrefined, a small amount of things like ores, concentrates, mats and precipitates. But we can see the sort of the orange there is the waste and scrap, and that sort of big wedge that sort of really starts in the 70s and reaches a peak in around about 2011. Right. So what this shows is that clearly, just based on what's coming into the UK in terms of these particular forms of copper and what's leaving the UK, is there's a clear net excess of exports over imports. And this is quantified based on going through, and the team spent a lot of time unpacking more recent evidence to understand copper content and variability that we could possibly apply to that. So it suggests that the UK has actually been the equivalent of a large copper mine exporting about 200,000 tonnes of copper or more for about the last 20 years. And on its own, that's an interesting number. But of course, there's always going to be more to that. So if we're looking at what that means, we have to think back over the industrial history. So we spent some time, the team delved into looking at the different facilities, and these are just the key facilities. We can see that the final copper refinery at the James Bridge Works closed in 1999, which of course is when you start seeing this big rise and peak towards 2011. Now, after that, after 2011, there were changes made, and basically any copper waste and scrap couldn't be sold for cash anymore. The mining boom had also gone bust, and so that peak dropped quite quickly. And so we're seeing a gradual decline ever since. But what this highlights is that part of the reason we're seeing this big increase in copper waste and scrap is because we don't have the facilities here. So, and I guess there's certainly some companies that are looking to do that. But I guess that's part of the thing, is understanding that history and understanding what that data really means. So you can see right there. If we look at the actual, forms and where that goes, we can find some data that looks at, it's mainly refined copper, brass alloys, and so on. And we think if we go through the whole history, that 100 years, just over 31 million tonnes in imports and just under 15 million tonnes contained in exports. And we can see that difference in the value over about the last sort of 5 years, 10 years or so, roughly about just over £1 billion of value for waste and scrap. But the contained copper for that waste and scrap is worth about 1.45 billion pounds. So about 390 million pounds worth of value leaking out there. We could see in the graph here that basically it's the change over time. Although China used to be the main recipient of a lot of that waste and scrap, more recently we've started seeing it going both to Europe and also the Asia Pacific. So when we set out with this project, we didn't exactly know where we'd end up, but what we've achieved is a really good understanding of this long-term trends in the copper coming into the UK and copper leaving the UK. There will be other forms coming into in manufactured products and components and so on coming into the UK. So what we've done is only a partial sort of material flow analysis, certainly not a complete one. That would require a lot more work. But if we're thinking about what that means, with the Vision 2035, the UK Critical Mineral Strategy, we do have ambitions around things like the extent of recycling, domestic production, and so on. So we think that this suggests an opportunity for certainly to increase the circularity of copper. But again, at the moment, one of the other things we've found is that some of the data that we're dealing with, there's still some gaps there that we need to work out how to address in the future, and so that we can actually continue to build towards complete material flow analyses. So I'll leave it there, and it's time to hand over to Jo Wragg. Thank you.
Thank you, Gavin. I'm just going to share my screen. It might take a second, so I apologise. Can everybody see that? I will assume you can. So I'm going to talk about assessing the copper and what the waste and scrap flows in the UK are and mean. Apologies, I don't seem to be able to move my slide on. Let's try again. Yeah, sorry about that. So the study demonstrates, as Gavin said, that there's significant opportunities. We've chosen to focus on copper because it sits across multiple sectors, so decarbonisation, technology, digital infrastructure, water supplies, etc. And that fits across many of the UK policies and strategies. There's multiple benefits to recycle copper, from financial, environmental and driving innovation. And you can see these by some of the icons that we've created. And you can also see that there are pros and cons of recycling and moving things around. From a purely monetary standpoint, as Gavin said, we currently export waste and scrap valued at 1.06 billion, but it actually contains 1.45 billion pounds worth of copper. So we, as a country, are losing out. Moving on to the supply chain and demand, there's an increasing demand for copper to meet societal needs and in this increasingly digital world, but to keep up with energy transition technology. And as I've said, we are currently losing about 390 million pounds of copper value a year. And what we've seen is that if we reprocess copper and recover copper, it can reduce the domestic supply chain vulnerability. Apologies for that. If we look at industry, copper is one of those transitional elements. It's transitional to foundational emerging technologies, from batteries to offshore wind and hydrogen, robotics and advanced manufacturing. And the supply of copper to these technologies is vulnerable to external competition from other countries who experience the same increase in demand. Therefore, to supply our homegrown recycled copper would have multiple benefits to the UK. And these include feeding the demand from the energy transition, reducing the vulnerability of the supply chain, driving innovation in product design and manufacture, and feeding the advanced manufacturing sector. If we think about energy, the UK transition to net zero can't be achieved without securing copper supplies, as technologies such as wind turbines, solar panels, heat pumps drive this copper demand. And understanding and growing the copper waste and scrap flow sectors can support the UK to keep up with the demand as new technologies are developed and come online. Another key point is that the energy demand required for recycling purposes is always reduced compared to that for primary production. Moving on to infrastructure, we currently don't have a domestic supply of primary or secondary copper. And to achieve what we want to achieve, we require recycling infrastructure to avoid vulnerability. All of our infrastructure contains copper to some degree. So to support current needs and the government's ambitions of, for example, the 1.54 million houses that it would like to create during the lifetime of the Parliament, copper is needed, and the ability to recycle copper streams is required. This is required for providing clean water through copper pipes, securing domestic supplies of energy, connecting houses to the grid. If we're going to produce all these, build all these new houses, they need support from various sectors. So, this is where we get a demand for copper in the UK infrastructure crossing multiple sectors. And the costs of infrastructure development are subject to supply chain instability, and this could be reduced by having our own supply. Having this supply supports upgrading of digital infrastructure. It improves circularity of supply, and it contributes to a water supply infrastructure. And these are just a few things that it's important for. If we think about globally, a secure supply of copper and understanding of the circularity shapes our trade and global cooperation, and it reduces vulnerability to geopolitical tensions. It also reduces the environmental impacts in other countries, extracting primary copper and reducing the amount of copper that we would send to other countries with lower environmental legislation. So it will reduce that volume. It allows the implementation and investment treaties which protect mining agreements, trade agreements that reduce tariffs and ensure predictable markets, and the UK to fulfil its obligation to organisations such as NATO. And if we produce our own, less vulnerable, but enough to support infrastructure, we don't need to rely on unpredictable markets. Moving on to innovation, understanding the flow of critical materials and our ability to recycle materials helps us with innovation, design of energy transition technology, innovation in recycling, so including designs for recycling, manufacture and recycler collaborations, AI, innovation and monitoring, which is going to be talked about later, and innovation in district heating. We need copper for all of these purposes. Moving on to the environment, understanding the copper waste and scrap flows impacts our environment, potentially more than we would immediately imagine. And it also and it impacts on our protection of the environment in multiple ways. For example, it's important to understand the location of copper waste in order that we can mitigate against environmental pollution. For example, flood mobilisation from contaminated scrap piles. Primary copper mining is energy intensive and environmentally disruptive, and without domestic supply, the UK does rely on overseas imports from countries with high water stress and often lower environmental control. In addition to that, access to this resource requires long distance transport, which has its own impacts on the environment. But there are opportunities to reduce dissipation losses, improve extraction and separation, and design products for disassembly, all of which support a more sustainable material cycle. So improving copper recycling can reduce the burden on mining countries. It can reduce the risk of soil and water contamination, supports clean water supplies, reduces emissions, energy consumptions, and improves supports increased sustainability of circular resource recovery. We do have some economic and ethics to consider when we're doing this. As Gavin says, the UK is losing both material and economic value that could support domestic supply. there is the loss of value by the exporting of more copper. Apologies. Exporting more value in copper than we have. We are thinking about the ethics again. Recycling of the copper increases revenue. It can reduce project costs and waste. It contributes to the circular economy, strengthens the UK competitive positions in terms of global clean technology supply chain, and it can support jobs in recycling facilities and all other support services. So in summary, by understanding the waste and supply flows, we can reduce environmental impact, we can increase security of supply, reduce vulnerability to geopolitical tensions. It helps support increased demand in decarbonisation. We can recover revenue currently lost in exported copper waste. Recycling would help keep up the supply for energy. But it would also provide an opportunity to invest in UK recycling infrastructure and building, which is one of the drives of the government. And it can drive innovation in product design and manufacture. And apologies for my stumbling, but thank you for listening. And I will stop sharing now.
Thank you very much.
Yeah, thanks, Jo. And over to yourself, Holly.
Excellent. Thank you very much. So just bringing up the next project. Okay, so I know it's already been said, but thank you all very much for joining us this afternoon. It's lovely to have you here. So I'm Dr. Holly Elliott. I am one of the leaders of the Future of Digital project that we had this year, but it was very much a CMIC team effort. So just to give you a little bit of background information, the modern world is undergoing a digital evolution at the moment, and that's really being accelerated by two things. One is the availability, and second is the reliance on data. But actually, things like artificial intelligence are becoming very much general purpose technologies. They're starting to become used in our everyday lives, as well as being used for more specialized applications as well. Now, data centers are having to grow as an accord to that. So they are being required to cope with things like increased data management, but also AI processing as well. And lastly, quantum computers are quickly progressing from things which were previously research curiosities onto actually being developed into prototypes. And these really have the capacity and the capability that far outpace anything we've seen before in terms of classical computers. So these three technologies together are being designated as frontier technologies by the UK government, but they're also being designated as critical national infrastructure as well. And that's really because they are key to the economic growth of the UK, but also very much key to UK security as well. But as the demand for these technologies are increasing, the raw materials that we need for them are also increasing as well. So that's why this project came about. And the aim of the Future of Digital project was to identify those raw materials, the need for the digital technologies, their future demand, and also where we might sit within the supply chain for those. So I've already said three areas in which we're focusing on. The technology was data centers, artificial intelligence, and also quantum computers. And we looked at the raw materials for these, but also the high purity and the isotopically pure materials that go into them as well. We looked at current trends, so how demand is increasing, the future trends associated with these, and we mapped out the supply chain. That's both in terms of global supply chain and UK capabilities as well. But within that, we looked at risks, we looked at bottlenecks, we looked at challenges, and also where there might be opportunities for the UK going forward. So just to introduce the first technology to you, and these are data centers. And these are essentially facilities that are constructed to house computer systems. So we're talking storing, processing, and also manipulating data. And they're really fundamental to economic activities here in the UK, but also public services as well. So I'm talking things like financial systems. It could be something like patient and employee records and storage as well. And really the type of data center that you have and their requirements vary depending on who owns it, the scale, the function, and also their operational resilience as well. So if you haven't come across that term before, operational resilience is essentially the data center's ability to maintain operations, to recover quickly following any unexpected event. So that could be a cyber attack, it could be a power outage, it could be some form of natural disaster. So essentially how quickly they can turn back on. And data centers are complicated bits of infrastructure, but they comprise of servers, networks, memory, cabling, power, cooling, the physical structure in which they sit, but also the security associated with it as well. The one thing that we didn't look at in this project is the construction materials in the buildings in which they're actually housed. So moving on to artificial intelligence, this is essentially the science of creating machines which have the capability to learn, but also to undertake tasks that usually require some form of near human intelligence. And they have quite a wide range of different applications and also abilities, which they're categorized on. But that could be anything from scientific modeling, it could be generating media content, it could be automatic cars in the future, virtual assistants, even things like detecting medical conditions and screening in the future, and things like speech recognitions as well. Now, they consist of a number of similar things to data centers. They require a computer interface, they require network, memory, also power, and also cooling as well. So very similar to what we saw for data centers. But these are very material intensive technologies. So as you can see from the image on the right hand side there, which is the periodic table, you can see that a lot of the material requirements for data centers and AI sit within the servers and also within the memory storage. If I just bring up my laser, so the servers and also the memory storage in there as well. And some examples of that are things like silica, used for semiconducting material, so thermal stability, fire resistance. Things like aluminium, which is quite lightweight, high thermal conductivity, very resistant to corrosion. That's used in things like fans and cooling. Copper is quite ubiquitous throughout. It's an excellent conductor. It's very durable, can be used in things like memory and cooling. But it also covers things like rare earths. So they're in permanent magnets, which go into servers, memory, power, and also cooling. But each data center needs something called an uninterruptible power supply. And that essentially is a backup energy source that bridges the gap between any loss of power and when the generators actually switch on. And that's usually something like a battery. So that means that battery minerals and elements are required for data centers as well. So we're talking things like lithium, cobalt, graphite, and manganese. And actually data centers require a huge amount of energy, sort of similar to an aluminium smelter in terms of the size. And they're currently using around about 2.5% of all UK generated power, and that's expected to increase to around about 6 to 10% by 2030. Now, traditionally, data centers have relied on water-based cooling systems. So that means that you've got large pressure on local water sources. But actually, lots of technologies are coming out now which require less water. And actually, 51% of UK facilities at the moment are using waterless cooling systems. And whilst the UK is expanding its data center footprint, actually it remains a net importer of most of the components that are required for data centers. We have good strength in terms of semiconductor chip design, AI research, and we have lots of semiconductor industry in the Oxford-Cambridge growth corridor down here. But the UK has got some very well established supply chains that can be capitalized by data centers. So we're talking things like strong capabilities in designing cooling technologies, photonics design for lasers, and also wafer growth as well. But predominantly globally, within the global supply chain, the UK is really seen as a design and innovation hub rather than a manufacturing supply chain at the moment. Now, moving on to quantum computers, they are essentially computers which use quantum mechanics to undertake mathematical functions of which classic computers are just incapable at the moment. And I'm not going to go into the physics behind it. That would take much longer than my 15 minutes that I have. But essentially what they do is they store data as quantum information, or qubits, if you're familiar with the term. And that allows for exponentially greater storage. And there are 7 different modalities or principles that are being used to develop this quantum computer technology. And that is superconducting qubits, quantum dots, trapped ion qubits, neutral atoms, color vacancy centers, photons, and also topological qubits as well. And what they're able to do is really to provide an accurate reflection of reality and also natural systems, which means that they're really good at applications in relation to simulation, optimization, and algebraic problems as well. So some examples of that might be traffic management systems. It could be future climate modeling. It could even be things like medical diagnostics and screening as well. But they're also capable of providing a series of solutions rather than just one. And these quantum computers require quite a wide range of different materials, but it depends on the modality that you are looking at. And all of these materials are chosen to avoid something called decoherence, which is essentially the decay of quantum information. And this periodic table on the right-hand side here shows all of the different elements needed for both data centers and quantum technology. And what you can see is actually that requirement spans the large majority of the periodic table, and there's a lot of crossover between the technologies as well. So some of the common examples we've already been through, like aluminium, silica, but they also require things like niobium, if you need any form of cryogenics in there as well to cool down to sort of 1 Kelvin or minus 273 degrees. You need things like helium as well. Non-linear crystals are required, and these are high purity, low defect crystals, which are used for photonic applications. And they contain things like gallium, silver, barium, germanium as well. So even range of those materials within things like the crystals. But actually these technologies require high purity materials as well, and we lack any significant UK capacity to produce these. And just so that you're aware of the terminology, 5N in terms of purity means 99.999% pure, so it's 5 digits, just so that you're aware of what's on the screen here. And some of the examples of high purity materials that we need are things like carbon, nitrogen, silicon, and these are produced in a wide range of different countries that you can see there. But the only one that we have any form of capacity to produce in the UK is actually small quantities of high purity nitrogen. In terms of isotopic purity, as I said, if you need cryogenics, you need things like helium-3, carbon-12 is required for synthetic diamonds, and also silica-28 that's required for semiconductor substrates. And actually the UK does have some capabilities in terms of silica-28 production, and that's through part ownership of the Urenco company, which is in the Netherlands. But to provide a UK context on quantum computing, the UK has the National Quantum Technologies Programme that really aims to bring together industry, academia partners, and also government stakeholders to actually evolve the UK into a quantum-enabled technology and quantum-enabled economy. But we also have the National Quantum Computer Centre, and there is a UKRI funded body, and they're trying to build 7 prototypes or test beds, a few of which have already been installed, and they're trying to work out the capabilities of these systems, determine which ones are more suitable to certain applications as well. We've also got the Scotland Critical Technologies Supercluster, and that was established to address 4 key technologies, and that's photonics, quantum, semiconductors, and also sensing and connectivity as well. But actually, we do have in the UK, as I said, some quite well-established supply chains that these technologies can actually piggyback on, such as telecommunications, photonics, cryogenics, and also semiconductors. And we do have some potential here in the UK to produce some of the elements that we need in terms of domestic supply. So things like rubidium and also cesium that are used for things like atomic clocks, gyroscopes, that could actually be produced as a byproduct of lithium production in Cornwall. But as we're increasing our future demand for all three of these digital technologies, we're actually increasing our demand for all of the materials that we've just discussed. And actually, many of those materials are already designated as critical raw materials. And they're not the only sector which are requiring these minerals. These are diagrams here which show some of the demands for the technologies that I just talked about, which is focused on the criticality assessment diagram that you'll probably be familiar with. And that is being compared to other technologies like batteries, renewable energy, and also aerospace. And you can see a lot of crossover between the two. So that means that there's potential for a lot of sector demand and sector competition in the future. But actually, a lot of these elements are produced as byproducts, so they're recovered during the processing of primary commodities. And that means their supply chains are much less responsive to demand. It means they're much more reliant on production of that primary commodity. The supply chains are also quite juvenile. They might be only produced by one or two companies on one or two sites, and that means there's a much greater risk to supply in the future. They're also quite concentrated, mostly produced by places like China, Australia, and South Africa, which again increases supply risk. But actually, we can't yet actually rely on the secondary supply of these elements yet. It takes time for these products to go into end of life and mainstream recycling to actually pick up to provide that secondary supply. But also skills are quite a limiting factor across a large part of these technology supply chains, from all the way from design up to engineer, and actually retention of that skill here in the country as well. But where there are challenges, there are also opportunities, and the UK needs to establish a foothold in the global technology supply chain to ensure that they remain competitive. And these are just some of the opportunities and recommendations that have been highlighted in the report. And that's things such as pairing data centres with renewable energy in order to reduce carbon emissions, make sure we're recycling heat that comes from data centres, and capitalising on domestic UK opportunities such as high purity and isotopic materials, that sort of midstream supply chain where we already have some expertise, ensuring that we have processing facilities that are domestic, recycling hubs that are domestic, and ensuring that components are actually designed for recycling. And that's on top of things like pursuing international partnerships, ensuring that we have skilled employees on all parts of the supply chain, and also making sure that we are able to retain that skill. So just to summarize, the digital revolution really is driving our demand for technological materials. It's also increasing the demand that is being placed on global supply chains. And a lot of those materials are byproducts. They have very juvenile supply chains, and they're also quite concentrated supply chains. And as there is demand increasing for technology, there's also demand increasing for lots of other sectors as well, like aerospace, renewable energy, electric cars. And although the UK should really endeavour to develop domestic supplies of lots of raw materials and try and establish UK supply chains where it can, we've got to be realistic in the fact that the UK cannot become a specialist in everything. And that means that global supply chains, international collaboration, and also strategic partnerships remain very much important. And the UK does have considerable expertise in lots of these different fields we just talked about: quantum computing, photonics, cryogenics, semiconductors, and that means the UK can really push forward with these opportunities in order to establish footholds in that global technology supply chain in order to remain competitive, but also to remain secure as well. So thank you very much for listening.
Okay, over to yourself, Pierre.
Thank you. Can you all hear me correctly? I think so. Fantastic. Right, so good afternoon, everybody. So already across the session, we've seen different perspectives on material that are considered critical to the UK digital technologies, their supply chain, and potential intervention for maximizing the value of the circular economy for a secondary supply of copper. And all these trends come together under the notion of criticality, which increasingly guide government strategy and industrial priorities. So this talk will focus on how we are currently improving the way criticality is measured to better support evidence-based decision-making. So the first couple of slides going to be a very brief reminder of how the last criticality assessment was conducted in 2024, opening first with the range of candidate material that is covered. So in the last assessment, we covered 80 plus candidate materials, which are evaluated under their diverse form, from ores and minerals to more refined products, such as chemicals and alloys, and exclude all the elements that are highlighted in green in this periodic table, as well as a range of industrial minerals, which are also listed here. To conduct the assessment, the full results of which and the methods are shown in this recap figure, we evaluated a range of indicators. And those were then aggregated into two different dimensions of global supply risk and economic vulnerability. The choice of the different indicators which are considered reflect our intention to evaluate as many stages of the supply chain, starting with the early stages, which are also referred to as the upstream, with the indicators like the mining and refining production concentration, also companionality. Then we move down the supply chain into the midstream. We enter the stages of manufacturing, which is best qualified for the UK in terms of defining for each candidate material our apparent consumption, as well as our net import reliance, and the gross value added for each of the sector into which the material is consumed. The international dimension of material flows under their different form is also captured by the indicator of global trade concentration and the UK net import reliance as well. It's at that time. The downstream or the later stage of the supply chain is partly qualified through how much the secondary supply through recycling can contribute to the supply of materials globally. So these indicators are then combined using various weights, and a criticality threshold is agreed based on stakeholder engagement with industry and government, resulting into the list which was published in 2024. So during our first public presentation of the results, we went through quite an in-depth discussion with all the participants, answering live about a third of all the questions in the Q&A, and published written answers to all the other, which are available on our website. But interestingly, most of the questions were obviously centered around the methodology and how we were capturing data. That was the most representative of the UK economy, for which a large amount of material is already contained in subcomponents and finished product. So this incredible engagement provided some very useful feedback, which formed the basis for our next methodological review, focusing on 8 key areas. So we expanded first our monitoring and qualification of the HS codes to better capture the flows of material in import and export for the UK and around the world. We explored as well the development of a range of metrics related to market sentiment, exploring various aspects of volatility, rate and amplitude and frequency of change in price data. We explored how to better qualify economic contributions of materials to different economic sectors of the UK, how to capture as well the influence of trade restrictions in global flows of materials, improve on the data already used for defining ESG credentials, explored as well if we could push the existing calculation of mining and refining concentration from a country level to the company level, and explore as well their ownership structures. We also spent a bit of time looking at ways to qualify in future mineral production, its uncertainty and how it compares with projected demand. In the next couple of slides, I will highlight some of the main progress and successful areas of developments, with all our results and discussion around this topic, which will be made available in our upcoming reports to be published online in a couple of days or weeks. So first, let's address an easy one with the expansion of our library of characterized HS codes. So HS codes are a standardized 6 to 10 digit numerical method, which is used worldwide to classify traded products for custom duties and taxes. So it allows about 200 countries roughly to uniformly identify goods being imported and exported, And for us, it is a fantastic tool to evaluate materials flows across the globe. But before we are able to do this, however, we need to quantify the amount of metal contained in each of those goods, which to transform a weight of good into a weight of targeted metals. And this is where the added expertise of geologists and materials scientists is required. So the first part of the supply chain is quite easy to quantify, but the increasing complexity of product and lack of descriptive terminology of the HS codes make this evaluation increasingly complex as we progress into the midstream and downstream. Nonetheless, we've made some major progress, moving from about 280 codes across 82 candidate material in the 2024 assessment, covering mostly the upstream, to an expanded coverage of just above 1,500 midstream codes that are spread across 41 commodity, which are the ones listed into that table. We've notably made quite a lot of progress as well in disentangling the group, which is well known as the rare earth element, into individual elements. And we plan on continuing efforts in, well, these cataloging efforts in the year to come, and this will play a major role in the data considered for multiple trade-related indicators and supply chain analysis. The next item on the list of improvement is the creation of a new indicator qualifying the information contained in price data for multiple forms of a commodity, either as a chemical, an oxide, an alloy, or a high purity form like the 5, 6, 7, 8, 9N that Holly was presenting. The idea for this was to extract a range of statistics from price time series to qualify whether the market for that commodity is opaque or transparent, for instance, if it is supply or demand led, and if we can detect any effects of market manipulations. For the UK, which is heavily reliant on import across diverse commodities, understanding market liquidity, stability, and transparency is essential to identifying where strategic intervention may be needed. So for this exercise, we focused on 16 commodities, which are representative of various market size, reporting practices, and different stages of the value chain to test the sensitivity and validity of the approach. The metrics that we considered for each time series were calculated across a range of sliding window of trading days, with the aim to capture different wavelengths of market dynamics. So these include a range of volatility metrics, notably intraday variance with the Parkinson volatility and the corrected short-range volatility through Hodge-Tomkinson models. We calculated as well the length and frequency of unstable period or volatile period, the number of highs and low pivot points, which are those colored stars here on the top graph, and how many times these were true or false breakout or breakdown in the price of a commodity, effectively switching the price dynamic into a bear or a bull market, if you want. We also compiled absolute range of variation in price movement and used all that to produce a range of metrics. So I fully appreciate not everyone is into trading, but these are quite common metrics in financial analysis for the evaluation of a market and how it behaves if you want to either invest into it or if you want to buy from it, and therefore you need to define the more appropriate timing to do so. So the first new metric that we develop is the market turbulence one, which captures short-term volatility and price instability. And the second new metric is the market disorder, which provides evidence through the statistics considered of the, if you want, the coherence and reliability of long-term pricing information. It characterizes how trustworthy a price time series is. So these were computed for some of the forms of the test commodities to obtain a market sentiment indicator. As you can see at the top of this table, we find copper. They're all ranked by the market sentiment indicator score. And we see copper as the fairly high on both metrics, highlighting that the last few years have been particularly volatile for this commodity, and that this has mostly been driven not by supply, but influenced by external factor leading to speculative trading motivated by tariffs and hoarding behavior based on partly unfounded global shortage announcements. So this is why we have such a market disorder score on that one. So the current ranking that you're seeing here is relative and temporary, as the methodology need to be deployed on a much larger range of commodities and explored across their different forms before the score are normalized relative to one another. But it serves the point of the demonstration that we can extract some quantified value that goes beyond a simple volatility index on the state of the market that we can use as an indicator, which will be allocated to the global supply risk dimension. So we now switch from the global supply risk more to the UK economic vulnerability with two new indicators added to the previous existing three. So these indicators were developed following the release of new data sets by the Office for National Statistics that allowed us to go further than the gross value added for each consuming sector, which we reported before, which is an approach which until now could not appropriately characterize how different industrial sectors are interconnected through supply and providers relationship, and therefore how a potential disruption could propagate up and down supply chains. As an example, we are now capable of establishing the material and energy requirements associated with the manufacturing of steel, which is a major consumer of iron, carbon, and a lot of other alloying elements, as you can see. And we can calculate, obviously, its direct gross value added, its GVA, and how the steel produced domestically feed into various advanced manufacturing sector and how much steel is otherwise imported for these sectors. From a stress perspective as well, this is a key development, as we can now better appreciate how a disruption in one of the upstream supplier outside of the UK, for instance, or an energy crisis may cascade through the steel industry and impact the construction, automotive, aerospace, and other sectors. Inversely, we can now better qualify how much a desired increase in the production of a finished product based on policy announcements, say an increase in spending for the defense sector, could back propagate on all the supplying sector, identifying bottlenecks and area for competition for access to resources. So when we look at it from a network perspective, it's not a surprise that the largest UK industry sectors consuming raw materials are heavily interconnected as both supplier and consumer for one another's products, as demonstrated by this kind of woolly yarn figure. But nonetheless, among this high complexity, we can try to impart some order and simplify this network through various economic and supply chain metrics. So in addition to the gross value added of each sector, which we were already able to quantify previously, we are now capable of evaluating how central a sector is to UK domestic supply chains, exploring the balance between its output, consumption, and amount of backward and forward linkages to other sectors. We can also evaluate how the output and the GVA of each specific sector contribute to the output and GVA of the other sector it provides to, allowing for a much more robust evaluation of the economic importance and reliance on materials of downstream, secondary, and tertiary sector of the UK economy. Think effectively that, for instance, the value of copper is not only in the manufacturing of pipes and cable, but in allowing as well the distribution or network of our energy and functioning of all the electronics that we rely on to. So this indicator will therefore be added to the UK vulnerability dimension and provide a much more global perspective on systemic importance and risk for UK supply chains. Our next topic of interest was to explore how we could capture the increasing amount of trade deals, tariff, and export quotas as a new metric to influence our risk characterization in criticality assessment. The frequency of this intervention globally has skyrocketed in the last few years as the race to secure critical mineral supply is really accelerating. So exploiting the global trade alert online dataset, we've been able to analyze the frequency, scale, and range of both harmful and liberalizing interventions per country and per commodity, using our expanding catalog of qualified HS codes to target the relevant interventions. As the UK is dominantly a net importer of material, the focus was really put on export relevant measures that affect us from foreign nations, as otherwise inward intervention occurring solely within other jurisdictions do not directly affect us. So understanding partners' propensity to impose restriction is as important as understanding, for instance, production concentration. And static trade concentration metric often overlooked this geopolitical dimension, failing to distinguish between reliable partners and those that are likely to weaponize access to resources. So we've therefore produced a trade intervention factor that is to be applied as a weighting on the national level trade concentration indicator that was already incorporated into our previous assessment back in 2024, to reflect really partners' intervention history and their inherent interventionism risk profile, if we may say so. The final aspect that will be modified in the next iteration of the criticality assessment is that of the environmental, social, and governance metric, which is currently used as a weighting factor on the production concentration indicator. So the ESG risks was developed in 2024 on the World Governance Index, the Environmental Performance Index, as well as the Human Development Index. And this characterized roughly geopolitical tensions, human rights violation, corruption, emissions, and biodiversity losses, amongst plenty of others. And these can all directly disrupt production, constrain market access, and increase operational costs. Effectively, poor ESG management can trigger community opposition, litigation, investment withdrawal, and regulatory barriers. The 2024 criticality assessment is among one of the most comprehensive in its integration of ESG risks, but there are still gaps that remains, particularly around future climate vulnerability. So we reviewed a large range of open source and commercial data sets and found that country-level data remains the most practical approach, despite limitations in capturing subnational and site-specific risks, which may vary strongly between geographic areas, climate, and commodities within even a single country. Unfortunately, most of the commercial and open data set we found usually have fairly limited geographic and commodity coverage, mostly tracking only publicly listed company, which represent 40 to 60% of world production for major commodities, and even less for minor metals. We had a similar range of issues for another indicator, which I will not present here, that the team tried to develop on the corporate concentration and ownership status, but effectively the data quality and the coverage were similarly insufficient to be used at the moment. So we were able, nonetheless, to incorporate a new data set in our composite ESG indicator, which is the Notre Dame Global Adaptation Initiative, or ND-GAIN, which captures climate-related exposure and readiness to adapt to climate change. It's a way to incorporate how, for instance, future water stress may limit mining and refining activities, either due to direct limitation in accessing water as a consumable. It can also qualify the impact of such consumption on nearby communities and activities, or the limitation for a plant, a refining plant, to access energy if those energy sources are related, for instance, to nuclear or hydropower, which can be all impacted in periods of drought. So in conclusion, all the very briefly described improvement I discussed into the previous slides are summarized in red here in this update summary for potentially the next criticality assessment. It's also worth noting that the benefit of our HS code catalog expansion on indicators relying on trade data such as the global trade concentration, UK apparent consumption, and net import reliance will be massively improved. notably drastically on the monitoring capacity that we have over the midstream flows of materials into the UK economy. So if the previous assessment made use of more than 1 million data points, the planned increase in data volume from this progress actually will only be able to be addressed through the development of databases and data processing pipeline that we will be developing in the year to come to automate really a large part of the data download, processing and quality check exercise. And this will allow us to spend a lot more time conducting sensitivity analysis and providing more detailed and tailored analysis to government and industry. As to when the next assessment is going to be conducted, that remains to be decided by government, but we would advise for a revision in 2027, which would be 3 years after the last one was conducted. So that will be it for me, and I will end my slides here. Thank you very much.
Okay, thanks, Pierre. It's toggling. So I think we've heard some great sort of presentations and sort of showing the broad body of work that we've been doing this year. There are still some other projects that we've done this year, but I guess these are really the principal ones. So happy to open it up to Q&A now. Unfortunately, I can't actually access the Q&A. I'm not quite sure what's happening. It was working before. So if I could ask either, JP, who's from our BGS, will be helping in the background there with the Q&A process along with Annabelle. Yeah, if you just read the question out, please. And then, yeah, we can go from there. Here's JP.
Hi, everyone. So we've still got 130 people on the call, which is fantastic. Thank you very much for joining us. And thank you very much to all the presenters for your presentations. I certainly found it very, very interesting. So we've already got a couple of questions in the chat. Just a reminder that a recording will be available, and any questions we don't have time to answer or can't answer live, we will paste on our website. So the first question we've got here is from Shan, and it's to yourself, Jo. She says, Jo, really interesting, thank you. Are there any environmental impacts from recycling copper? For example, chemicals used for copper extraction?
Yeah, I think there are quite a few questions that need to be asked. One of them relates to other elements that are associated with the recycling waste. So it could contain other materials, toxic metals, harmful metals such as lead. In terms of extracting, I think the extractant that you use would depend on the metal content. So what mixed metals are there and what's most appropriate. But yes, there are potential problems, and we need to understand the waste as a whole.
Right, thank you, Jo. I don't know if is there anyone else who would like to jump in on that from the panel?
Yeah, I could just add some extra thoughts there as well. Like I think a lot of the industrial facilities, like a secondary copper refinery, we know how to operate them well. If we look back in the UK history, we've certainly been operating facilities like that for close to a century or more, really. So I think a lot of it is just having a lot of the standard risk assessments, all of the monitoring in place, and making sure that the management is really up to the sort of expectations that the communities and governments expect.
Great stuff. Thank you. The next question says that I feel that many groups around the globe are doing very similar work. I think this question came in while you were speaking, Pierre, are doing very similar work, trying to quantify critical raw materials content in all kinds of products and half products. Seems to me a great opportunity to join forces.
Effectively, and we are already doing that. A lot of the starting work for this cataloging exercise was done effectively by the Screen project in the EU, and we've expanded on it, carried on expanding on it, and we are in close collaboration with our equivalent agencies in Germany, in France, and other places to effectively exchange continuously on the progress that we're making, checking on how we come to similar conclusion about effectively this data exercise. But it is a very long process, and sometimes there's polite disagreement, but we try and keep a strong record of all the sources that we have, and we try always to apply the data to that of the UK, because for various reasons, the same code might be considered as more or less rich in different countries based on effectively their import from different sources for the same product, which may vary in their characteristics. So there are going to be some slight differences, but we are collaborating a lot already.
Great, thank you, Pierre. The next one, probably for yourself, Gavin, I'll certainly start with. Is there anything you can say about the quality of scrap and how that might or might not limit recycling to high purity copper?
One of the challenges is that we don't actually monitor or measure the copper content. And sometimes when we're dealing with things like refining or secondary refining, it's not so much the copper content, it's the content of other impurities that can be probably just as important and sometimes more important, actually, because that cuts the heart of either cost, whether it's of other impurities that require processing or waste management. So now, based on what we see in terms of copper materials, and there's some data around that allows us to sort of accurately sort of estimate primary supplies of different copper forms, alloys and so on. And we know the types of uses that copper goes into, whether it be cabling, whether it be piping, electronics, and car components, and all sorts of things. So there's certainly some ways to sort of come up with some approximations of things, but directly we don't monitor it, and so I think that's one of the gaps that we have, and that's not the only area. There a lot of trade codes. We often have to make assumptions around what the actual content of that particular trade code is. So. But we think we can, confidently say it's probably around about 90%, maybe a bit higher, maybe a bit lower. But I think the other thing to remember is it's not just about the copper content, it's also about the other things that are there, which may be both good and bad as well.
Thanks, Gavin. Jo, I'll start this one with yourself, but I'll open up to the whole panel as well. Have you done, or are you aware of any studies around the cost of setting up a recycling plant? This came in during the talk on copper.
No, I'm afraid I don't know. Sorry.
Yeah, I can help there. I think we do know there are companies out there looking to build sort of secondary copper refineries. We haven't done the analysis or looked at sort of information that looks at that sort of financial case. And I think there's certainly companies are in the process of doing that. So I think the opportunity is there. There's certainly some companies out there that recognise that, but that I guess is not part of our remit.
Thanks, Gavin. Oh, sorry,
I think
Pierre.
Effectively, the cost of running such an operation will depend on the stream of materials. So we need to put in place first the different areas of collection and separation to extract, really valorize the waste. And then it was going to be pending the price of energy, what's the source of the energy at the time that we're running. So there's lots of variables and we can explore that further down the line, I think.
Pierre, I think this is another one for yourself. So the UK criticality assessment is very detailed. Do you have any advice for how the layperson might be able to best translate it and understand it?
Yeah, so we try our best effectively to give some interpretation to the public and industry and policymakers to effectively how do we interpret all those complex metrics and math. But it's really it's a communication exercise that we're trying to get better at. All those different indicators are potential dimension, and each and every one of them is important and can be the focus point onto which people that want to make a change in trying to de-risk their supply chain need to look into what they consume and what are the parameters which are being flagged as red into our reports and data tables, and try to make a difference there. But effectively, the way to interpret criticality is a material that will have a high criticality can be for a lot of different reasons, and that be because of difficulty in the production or potential bottleneck, or effectively potentially its importance to the UK economy and how a minor disruption could potentially have very large impact on the global economy. So that would be the way to generally interpret criticality, but if there is a need for more detailed explanation, I'm happy to provide.
Brilliant. Thanks, Pierre. The next one for yourself, Holly. So particularly in light of your presentation on the future of digital, who would you summarise are the priority partners for the UK, or some of this priority supply chains might be a better way of phrasing that?
The government has obviously got their own criteria about who they might choose as strategic international partners, but I can touch on ones that we have covered in terms of projects for British Geological Survey. So one, for example, is Canada, who is already an international partner for the UK. And there's a series of different opportunities for critical minerals there. So, for example, you've got the rare earth processing facility that's recently been set up in Saskatchewan. And we've been looking at sort of rare earth pegmatites up in the north of the country, where they might be able to develop a stream of monazite into that. Now, that's obviously going to hugely diversify the rare earth supply chain, which will make it much more resilient in terms of supply, and also reduce the risk in terms of actually being able to get supplies of these quite critical elements at the moment. But there's also other places that we can look at, like Angola, for example. Now, Angola has the Lobito corridor that runs through it, that goes all the way from places like the Central African Copper Belt, that allows critical metals like cobalt, for example, as well as copper, to actually be able to shipped out to the western part of Africa, and that makes it much easier to get into the Western markets as well, instead of heading over to places like China if it's shipped over to the east. So there are very many different areas that we can look at, but it's in terms of having strategic partners in the future, it's going to be about who has the critical minerals that we are looking at that we can't produce domestically, and also where are there stable geopolitical regions that we can actually access, and how can we get them over to the Western markets.
That's great. Thank you, Holly. Gavin, I'll start this one for you. So the question asks, the copper waste metrics are compelling. Given the financial and environmental risks associated with starting or reopening a copper mine, does the panel agree there is strong strategic justification for exploring better utilisation of our above ground resource first?
Yes, I think is the very simple answer. And apologies, my camera keeps turning itself off. I have absolutely no idea why. It wasn't doing that before. But yes, and I think that's the sort of the point between myself and Jo. I think it's a very good case study of actually that exact opportunity. So I think there's a lot of good merit in pursuing that, definitely.
Thanks, Gavin. Pierre, and to the wider panel, thank you very much for this interesting presentation. This attendee has two questions. The first one, concerning the ethical considerations of copper recycling, what strategies are considered to promote it? And part two, regarding the ESG criteria on criticality assessment, does the ESG also include the social license for critical mining operations, given the global trend of increasing local conflicts against mining companies?
Complex questions. So I'll start with the ESG maybe. Effectively, the license to operate is probably one of the major hurdle that mining companies face for the development of a potential deposit. Unfortunately, we cannot really incorporate that at a national level, although I mean, we cannot incorporate it at a project level or company level because the data simply is not there. And effectively, it will depend on each company and each project. It's the way they approach the development of their projects in their development, and effectively, they are encouraged to get in touch with the populations at the beginning of the process, not start doing all the exploration and resource characterization and mine planning before actually starting the consultation exercise with the local population. This is certain to result into a blockage. Effectively, you could argue on the flip side that the social license to operate is a lot already directly reflected into the governance standard and the access to the largest countries that are already large producers. So effectively, that will be a way to see it. On this first question on the ethical consideration of copper recycling, effectively it's a way for us to minimize primary extraction. Strategies are considered to promote it. This is unfortunately not for us to comment on. This is more a policy related discussion. So effectively we are highlighting potentially where intervention can be done and how those need to be put in place. That depends on a lot of other factors, on industry partners and how the government supports those actions. I don't know if other people in the panel wants to comment further.
Yeah, happy to add some extra thoughts there. I think certainly, you know, that management of a copper refinery would have to consider both the energy cost, the social license, and all sorts of other factors, and they're fairly normal. But again, there's anything sort of broader, more policy related. That's, I guess, for government to consider. I think on the sort of social license question, I think some other sort of thoughts that I think we have to acknowledge is that can be supported. I think one of the big challenges is a lot of communities are perceiving that critical minerals is becoming an opportunity for projects to be developed fast without as much rigor and without as much, say, social license. Now, there are ways to address that, but they involve resourcing. They involve resourcing communities to engage in processes so that there can be that shared understanding of projects and make sure they're designed properly, they're looking to be operated properly, they've got confidence in the regulatory process. But regulators also need to be resourced so that these processes can be delivered in a timely manner. So I think there's ways to deal with that. But I think that's what's really, really important, is that we have to acknowledge that social license needs to be given that sort of credibility and resource to make sure that these processes do achieve positive outcomes and don't repeat mistakes of the past.
Brilliant. Thank you. Thank you both. Obviously, a lot of the people attending are really interested in copper. We're getting a lot of copper questions. Gavin, Jo, seeing as you both did your presentations on copper, there's a more general question here about what you think might be the main barriers to the UK recycling more of its copper. Jo, I think in your presentation you recognised there was a big potentially opportunity. So what do you think get in the way of that?
I think as much as there's an opportunity, we have to think about what the barriers are and how to mitigate those. I think part of it is understanding what is actually in the waste, because it would be mixed waste with metal. I think infrastructure development, we need infrastructure to be able to do it, but it's where would we put that infrastructure? And the environmental impact, I think that they're quite important. And obviously cost. What is the cost benefit of us doing it? But that they are decisions for the government to make rather than us, because it's certainly outside my expertise.
And Gavin, is there anything you would want to add on top?
Yeah, I think we lack the facilities. So I think we need to make sure we've actually got that infrastructure, as Jo was sort of talking about. But as part of that, we have to make sure we understand what the energy costs are, and looking at the sort of the broader suite of the logistics chains and all sorts of things that go around that. So the infrastructure is both the facilities, but then also the logistics that helps collect the materials and transport it to the sort of, say, the secondary refinery and so on. So they're all of the things that we have to make sure we look at, and certainly that's sort of there are companies out there doing that.
Great, thank you both. This next question for yourself, Holly. So the presentation has mentioned the possibility of cesium and rubidium production as a byproduct of lithium processing in Cornwall. Is this something that is in the pipeline, or are there other projects that are not widely known that have the potential for byproduct recovery besides the main metal product?
Yes, that's a good question. So as part of Cornish Lithium's project down there, They are looking at the possibility of extracting both rubidium and cesium at the same time as they are processing the mica for lithium. And I believe that as part of their pilot processing plant, they are trying to get samples of potential byproducts to see whether there is possibility to financially extract them at the same time. However, when it comes to these byproduct recoveries, there needs to be economic viability. There does need to be a fully developed demand market for them as well. And as I said, there's lots of potential applications for cesium and rubidium in the future in terms of these digital technologies. So once demand for them ramps up, there is a high possibility that it might actually become economically viable to extract these as byproducts from the lithium processing. Now, in terms of other projects, it is highly recommended that any mining project that is going ahead does take advantage of that full value mining view in order to determine whether there are any byproducts that are present that might need to be extracted at the same time. But of course, it does have to be looked at with an economically viable viewpoint as well. And it might be that incentives are required in the future in order to actually ensure that companies do go down that route of extracting every little bit of value that they are from their mining projects.
That's great. Thank you, Holly. Pierre, so this next question I'll direct your way, but it might actually be outside of BGS's remit. Could you provide an update on the growth minerals list and how that work will continue / the methodology will evolve?
So effectively, the growth mineral list is an addition that was led by the Department for Business and Trade in collaboration with other government departments during the publication and the development of the UK Critical Raw Materials Strategy. So it's our understanding that they've defined the growth minerals as those minerals which are essential for the activities related to the industry sector, the 8 industry sector that are considered the most important for UK growth. So you will find a lot of overlap effectively between the critical mineral list and the growth mineral list, but they are to some extent slightly different perspective. The critical mineral list is very much what's critical at the moment, and obviously given the trends in technological development, it is very relevant for the future. The growth mineral list is very much focused on what we think we will be needing in the future for those areas globally. So they partially strongly overlap, but the methodology are very different effectively, and this work was led by DBT. So we do not necessarily know the frequency at which they want to update that or how that's going to evolve.
Thanks, Pierre. The next question comes from an attendee who's joining us from South Africa. So thank you very much for registering and joining us. They would like to know, and Gavin, I'll direct this to yourself. They would like to know, how is the British Geological Survey integrating geochemical, geophysical and remote sensing data to improve the identification of critical mineral deposits in unexplored regions?
Yeah, thanks for that question. I guess it gets to the heart of a lot of what a geological survey exists for. Everything starts with a rock. So understanding those rocks from the various ways, whether it's through geochemistry, whether it's through geophysics, and the where you find these accumulations of elements such as critical minerals that are worth mining. So there's various ways we're involved with that. There's work we're doing with some surveys in different parts of the world in terms of setting up the data infrastructure to house things like geochemical databases and geophysics and so on. Certainly in the UK, we have regions such as the TELUS program in Northern Ireland. We have the TELUS Southwest around Cornwall. And we'd certainly like to see more geophysics and geochemistry rolled out across the UK to help support, I suppose, the next generation of mineral exploration that could find new deposits for things that we haven't really looked at or looked for in the past. So there's various ways that we do that, and I guess that's a lot of that is, especially our international work done by our colleagues here at BGS. A lot of that is done in collaboration with the various geological surveys or their equivalents in different parts of the world. But yeah, hopefully that helps. Pierre, you've got some extra thoughts there, or Holly?
Yeah, just wanted to add that effectively for the UK or internationally, the BGS support different types of what we call prospectivity mapping, which is the the exercise of combining different types of data, whether it's geochemistry, geophysics, geology, remote sensing, into heat map that highlight potential targets for future exploration. There are lots of different ways that we do this. We approach that from the angle of an expert-driven approach, where we use our knowledge to guide our interpretation on data that we already know, or we also develop different machine learning algorithm. We are currently using an array of them as they provide different metrics and different quality of predictions. So we are invested, obviously, and we're developing the skills and methods to do this kind of prospectivity work. And as Gavin said, we are very much looking forward for more data to be acquired for the UK.
Brilliant. Thank you both. I'll ask this next question to the panel. Thanks for the presentations. For many critical raw materials, developing recycling needs a regular feedstock over a period to enable the investment in facilities. Is there any consideration of how the UK could work with other countries to help establish good waste feedstocks, bearing in mind waste movement restrictions?
I'll have a start at that. I think under the Vision 2035, the UK strategy, international partnerships are a fundamental pillar. Now, the UK can't do everything on its own. The EU obviously can't do everything on its own. I don't think there's any country that can do everything on its own. So a lot of it comes down to understanding the different strengths that different countries have. And so the processing facilities could be built in, say in the UK, and that processes streams from across Europe. Or we could think of other alternatives along similar lines as well. But a lot of it, I think, and this is one of the really important points, is understanding the data, making sure we're monitoring the right things, making sure we're actually measuring things where we can, and then using that to basically drive, these sort of circular approaches. So I think that's, a large part, I guess, of a lot of the effort from our team here, both at BGS and also in CMIC, is mapping those supply chains, mapping those flows, and working out the quantities involved, so we can actually start to facilitate these things on a much larger scale. So hopefully that helps. Any thoughts from others?
I would potentially comment in stating that we are also doing a lot of work on foresight, so that we actually have an idea when those stocks, as to our future use of some upcoming technologies, when those stocks are going to accumulate and reach their end of life, and effectively when we have an idea as to when there will be enough material to justify the creation of recycling facilities. And effectively a lot of collaboration needs to be done, so that not a single country bears the cost of all the recycling across all the metals. But this is a lot of work that is being engaged, doing discussion with the G7 and G20 at all the different levels.
Brilliant. Thank you both. Okay, we've got another copper question, and it's a follow-up to one of the answers that came previously. So the panel were asked about utilising above ground copper resource first ahead of reopening a UK copper mine as a strategic priority. And I think that received a positive response. Can the panel comment more broadly about complexities of producing high purity copper from recycling, and whether there are any means of assessing the environmental impact of this practice versus a primary / mined resource? Will the Critical Minerals Intelligence Centre investigate this further to inform policy going forward? So Gavin, probably one for you first.
Happy to give that one a crack. We know how to quantify a lot of the different environmental impacts, whether it be air emissions, water, solid waste, etc. Or methods such as life cycle assessment have been around for quite a few decades now. So we know how to actually compare, say, a primary mine versus, say, recycled copper. And that's why we say, we know typically, and we see this with aluminium and other metals typically as well, is that the energy content or the energy intensity of producing a secondary copper is less than primary copper. Now, there's some caveats to that. Not always just the same number. There's a lot of things that come into that. And sometimes energy is not the only metric that matters. It's things like the acid consumption, where that acid comes from, things like the greenhouse gas emissions associated with things as well. So a lot of these things we know how to how to make these sort of comparisons, how to do these sort of analyses, and certainly we've done some of that work in the past, both across BGS and a bit within CMIC as well. So it's something that's certainly not on our radar for the next financial year, but it's something that we'd certainly like to be able to explore further, because the being more systematic about valuing recycling and actually understanding the environmental impacts, what that means, and comparing them to primary, I think it's a key part of the justification for more recycling broadly. And again, the circular economy is about a lot more than just recycling, but it's certainly that is an important part. So certainly, yeah, it's something we'd love to do, but we're not looking at the moment in the next financial year. But certainly, it's something we'd still love to be able to do more in the future.
Thanks, Gavin. I don't know, Jo, if there's anything you want to add on top.
No. I think Gavin's covered it.
The advantage of going second and answering a question. Holly, this next one for yourself. To what extent does the panel think that companionality with a major potential constraint on supply?
Yeah, another good question. So when it comes to mineral deposits, you don't just get one mineral or one metal associated with it. You tend to have a wide range of different elements associated with them, but it tends to be that we go for the ones which are primary commodities. So that can be things like copper, aluminium, and then everything else that's in there as well is extracted during the processing stage as a byproduct, and we recover it if it is economically viable. So in terms of whether it's a constraint or not, I'm not sure you could say it is a constraint. It's definitely a factor that has to be taken into consideration, because it wouldn't be that we necessarily go for an extractor product which was just to get the tellurium out, when there's also a huge amount of other commodities in there, like copper, for example, that we can extract at the same time. So in terms of constraint, I don't think you can say that something being a byproduct is a constraint. It's more of a factor that has to be taken into consideration when we're looking at global supply risk, because in terms of actually getting these byproduct elements, it is very much dependent on the levels of extraction of the primary commodities. And as such, if supply goes up, then that means that actually our extraction of that byproduct element goes up, and therefore prices might be affected. Or it means that actually it might be that one mine in one country is affected by too much rain one year. So actually a large amount of our supply for a byproduct might actually crash, which would then mean that actually supply risk goes up, prices go up as well. So in terms of that question, I would say it's not necessarily a constraint, but it's a factor that we have to take into consideration when it comes to global supply risk and also price volatility in the future, and therefore all of the geopolitical ramifications that come with that.
Brilliant. Thank you, Holly. I don't know, Pierre, is there anything you would like to add at all? Nope. Excellent. Gavin, we've got another question here, which I think might extend beyond BGS's remit. But someone asks, has anyone worked out what the price of copper would have to be to make it economically feasible to recycle from available grades of feed?
No, I know that type of financial analysis is normally outside our remit. So no, that's not something we've looked at, sorry.
Pierre, this next one for you. The UK government, DBT, rightly has a focus on critical minerals, with CMIC, a critical minerals strategy, strengthening planning policy in the NPPF, none of which are currently mined commercially in the UK. However, is there any assessment of the potential GVA of critical minerals compared to the GVA of non-critical minerals, which are currently mined in the UK? Are of significant importance to delivering net zero, but which do not benefit from the level of support, research or investment provided by DBT and the wider UK government in terms of strategy or policy? Sorry, that's a long one. It's probably easier to read it.
Thanks for the question. So when we do conduct the assessment, we consider that all the commodities that are being assessed are candidate materials. So we do calculate the GVA and all the other economic associated metrics for each of those candidate material, and those are then aggregated and plotted into the criticality plot. So effectively, we do know those values, and those that make it to the threshold for being considered critical will get the status of being critical, and that means they have enough economic importance and potential supply risk for being considered, I don't want to say worthy of extra investment, but definitely bring more attention to them so that they can be de-risked. The difference effectively with commodities that are currently being mined in the UK domestically is that effectively they will influence the balance of how much we need to import of that, and effectively it's even more influential for industrial minerals, which are absolutely essential for the creation of all the infrastructures, road construction. But effectively, because they're very bulky material, they're always mined very close to the source of utilization. And effectively, we do not consider there is as high a risk compared to other metals. It's always important to consider that initially the criticality assessment is a ranking of relative criticality from the least to the most critical. But for the purpose of effectively industry policymaker and decision making, a separation is made somewhere in that rankings to actually focus the attention on a subgroup of material. It doesn't mean all of them should be equally de-risked through supported investment from government, but effectively the creation of growth mineral list, which incorporates some material which are not critical, is also an understanding that some actions are required as well on some other commodities. I hope that answers it.
Thanks, Pierre. The person that asked the question, if there's anything you'd like to follow up on that answer, please do post another question in the chat. But there is a follow-up question from another attendee, which I'll direct to yourself, Gavin. As the criticality assessment is evolving, the metrics used, does CMIC see there being significant movements of materials in their CRM position, or do you see it being minor adjustments? I mean, it might be too early to say either way.
Well, I think if you look at the history of criticality assessments that have been done over the last sort of 15 years, really, it's sometimes there can be changes. And I think if we look at the UK from 2024, the position of fluorspar or fluorine, we would expect to change from being not critical at all to being very obviously critical. Now, and that's simply because we've stopped mining fluorspar in the UK and we're now 100% net import reliant. So part of the nature of criticality is how dynamic things can be, how things can change. And so certainly when you look at either US assessments, EU assessments, if you go back through the various risk lists that BGS used to produce 10, 15 years ago, I think we do see these sort of changes. Now, part of our job, and I think this is one of the most important things to always remember about criticality, is it's not just whether something is critical or not, it's also understanding that commodity, understanding that supply chain and understanding the risks. Some supply chains are much more exposed to things like water stress, others are much more governance exposed, others are perhaps more socially exposed. So I think that's sort of part of the key things to always remember. And so going through a criticality assessment, that's part of what you learn is actually understanding the different commodities, the different supply chains, and the different risks that you can identify. And things change, and things can change quickly. So we've certainly seen that in the history of criticality assessments over the last 15 years.
I would add potentially one aspect that I highlighted at the end of my presentation is that we're developing a large database system and different automated pipelines for data integration, which will make us a lot more responsive in the way we can evaluate changing criticality values. Obviously, the next criticality assessment, because of the simple fact we've expanded the number of data we can consider, we're introducing new indicators. The results are not going to be directly comparable like for like, but what we can potentially do is run all these new indicators back onto the data that was considered back for the 2024 assessment and effectively see how that ancient exercise has evolved into the last few years. So this is something effectively when I was mentioning sensitivity analysis is we will be evaluating how those new indicators create changes and do we think they are more or less relevant. Last time we had various weightings applied to different indicators in each of the dimension, and that's also part of our expertise in trying to make sure that some of the indicators, the confidence we have into them is reflected in the importance they get.
Thanks, Pierre. Thanks, Gavin. Okay, this next question, I think for yourself, Holly, but also Gavin, maybe you want to come in as well. So it reads, I am a geologist with over 2 decades of experience in navigating the critical minerals and mining policies and politics in West Africa. I offer strategic interventions for interested parties operating from the National Brownfield Institute at Wolverhampton. I am currently accepting consultations for strategic discussions. How will CMIC, its friends, partners and collaborators utilise this opportunity to explore the possibilities in African markets?
Yeah, that's fine. I can take that one. Thanks. So essentially, when we look at a lot of our different projects that we've done, so Future of Digital, Criticality Assessment, and so on, we do look at global supply chains. So we look at where the critical minerals are coming from, who might be producing them, where they might be refined. So we do look at various different African markets. And we have done, as the past, we have looked at different commodity profiles. We have done different country profiles, which are available on the CMIC website. So we have looked at different aspects of the sort of the global supply chains like that. But actually, a lot of that work sits under our international team at British Geological Survey, which is mostly funded by the FCDO. And we do various different projects in various different African countries. For example, I've just completed a two-year one over in Angola, where we are looking at their critical mineral supply chains. I know that we have just had one completed in Zambia, where they have produced an atlas of critical minerals for Zambia. And those are all freely available to the wider audience. So those are definitely sort of exportable products, if you like, that the country can use, but also they can use as a wider investment tool to encourage people into the country as well. So I would say that mostly fits under the remit of our international team, and that would depend, where we look really does depend on priority countries for the FCDO at the moment. But as I said, we have done some work on supply chains in Africa and many of the other countries for CMIC as well.
Brilliant. Thank you, Holly. Well, I think that brings us to the last. We've got a couple of other comments and links, but not specific questions in the Q&A. So we've still got a huge number of attendees with us, which, thank you very much for staying almost the full 2 hours. I don't know if we should move to closing comments. If there's any wrap-up statements anyone would like to add from the panel?
No, I think thanks everyone for joining, and again, apologies for my camera. But I think one of the things just to note is that the coming year we'll be doing a lot more work around the automation of a lot of our data work, and thinking about some of the different technologies and things like that. So grid scale batteries is an area we'll be looking at. So, and there's some other sort of projects as well. So, so I think for us, and probably looking towards the next criticality assessment in 2027, which is gives it the 3-year cycle, which is fairly normal around there. But that's obviously the final decision on that is a decision for DBT. So I think there's still lots of work to do, and I think as we've seen, the criticality is a very dynamic area, and so it's important for us to sort of maintain the data sets, maintain the analysis, and therefore the support we give to the UK government. So, but happy for some other thoughts from Pierre or Holly or yourself, Jo.
All good for me as well. You've said it all. I think there's plenty of work, and we look forward to collaborating more closely with all the other people that are involved into this expanding area, and looking forward to producing some interesting analysis.
Great stuff. Well, we'll wrap up there. As we've said, there'll be a recording of this webinar on our website in the coming week or so, and a transcript of all the questions as well. So thank you very much for registering and joining us, and thank you very much to the panel members for their presentations.
No worries. Thanks, everyone.
Thank you.
Thank you very much, everyone.
Bye.